Welcome back to the lithium lecture. During the first part of this lecture, we have seen the different chemical and physical characteristics of lithium. We have seen also cosmological, geological, and geochemical aspects of lithium. And in the second part, we have seen the different lithium-bearing minerals with the characteristics of 3 of them. And today, in the third part of this lecture, we will see the different types of lithium deposits. So we can distinguish 3 main types of lithium deposits. The first type is pegmatite deposits. They are peculiar magmatic rocks. I already mentioned pegmatites in this lecture, and we will talk about them in details a bit later. The second type of lithium deposits are brine deposits. And pegmatite and brine deposits are the most important for lithium sourcing presently. There is a third type, sedimentary deposits. They are basically clay deposits. There's 3 deposits have economic interest, but there is also a fourth type. They are metasomatic deposits. They have been recently identified as a new type of lithium deposit. We will talk about them also a bit later. Lithium deposits in terms of resources and reserves, just to remind you, reserves are the total amount of valuable element or metal proven to exist and to be economic for mining at present. This is what we can actually get considering available technology and market price. Resources are the total amount of valuable element or metal that might be accessible if technology allows it. So back to lithium, we have 17 million tons of identified reserves. That's the figure for 2019. We have about 80 million tons of estimated resources. Again, that's the figure for 2019. The highest grades are in pegmatite deposits between 0.3 to 1.4% of lithium metal in these deposits. These deposits are easier to exploit owing the high grade, the size of these deposits, about 0.1 million tons of lithium in average, and they represent about 50% of the current production. But they represent less than 40% of the resources. The lowest grades are in brine deposits, but these deposits have the largest resources, about 60% of the known resources. Now we can look at the worldwide distribution of lithium deposits. You can see the major deposits on this map. The red squares are pegmatites, the blue crosses are brine deposits, and the green stars are clay deposits. Basically, what you can see on this map is that the major deposits are actually pegmatite deposits. There are also quite big brine deposits, especially in China and more importantly in South America. And finally, clay deposits are quite few in North America and here in Europe. Talking about Europe, you see that there are just a few major deposits. And if we look at the pegmatite deposits specifically, they are smaller than other deposits in the world. And I will especially talk about this giant deposit here, the Greenbush deposit. In terms of production, reserves, and resources of the major contributors, again, I give you the figure for 2019. Current reserves by country: Chile, 8.6 million tons; Australia, between 1.7 to 2.8 million tons; Argentina, 1.7 million tons; and China, 1 million tons. Basically, the main producers are Australia and Chile. More in details, you can see in this diagram. We have here on the y-axis the resources in kilotons, and on the y-axis we have the production in kilotons as well. So the main producers, Australia and Chile, they are clearly distinct from the other producers. The production in Australia is dominated by pegmatite deposits, while in Chile the production is dominated by brine deposits. The biggest resources, as I mentioned, are in brine deposits, but you can see here that these deposits, the brine deposits, are not fully exploited yet. Now let's switch at the main characteristics and formation processes of the different lithium deposits, starting with pegmatite deposits. You can see on this picture here the pegmatite body in the Ute mine in 1902, and that's the same pegmatite deposit in 2018. The main characteristics of pegmatite deposits. Pegmatites are magmatic rocks. They occur as veins and dikes between centimeters to several hundred meters thick, and they are formed during the very late stage of crystallization of a granitic magma, and that happens at quite low crystallization temperature, between 500 and 600 degrees. If we compare with the crystallization temperature of granite, it's about 900 degrees. A key feature of pegmatites are the very large crystals, between several centimeters up to several meters long. This is what you can see on this photo. You have a 4.5 meters long spodumene crystal from the Plumbago pegmatite. In this specific deposit, some crystals are up to 11 meters long. And from different studies, geochemical studies and logical studies, we know that this kind of very large crystals cannot be formed if we don't have aqueous fluids to feed them when they grow. We can distinguish two subtypes of lithium pegmatite deposits, the LCT type for lithium, cesium, tantalum pegmatites, and the other subtype includes other pegmatites and their associated magmatic and metasomatic rocks. In details, the LCT pegmatite deposits, they show strong enrichment in lithium, cesium, and tantalum, but they are also enriched in rubidium, beryllium, tin, and niobium. They have also significant enrichments in boron, phosphorus, and fluorine. Most abundant lithium minerals in the pegmatites, spodumene, it can represent up to 58% of a pegmatite body. That's the case for the Plumbago deposit. We can find also petalite, lepidolite, elbaite, a tourmaline mineral, and we can find also phosphates of the amblygonite monteprasite solid solution. And finally, in the metasomatized country rock, the host rock of the pegmatite, we can find onquistite. Just to show you how these minerals look like in a hand specimen. This is a picture of a petalite-bearing LCT pegmatite from Utah mines. This grayish mineral is the petalite. Here we have potassium feldspar, and here as well the elongated mineral here is the elbaite, a phosphate, and here the flaky minerals are mica. Another specific characteristic of pegmatites, they are mineralogically and texturally zoned. We can find up to 11 mineralogical and textural zones, usually 5 zones. But I will give you a more simple example with 4 zones, starting from the center of the pegmatite toward the host rock. And starting from the center, we have the nucleus, which is formed by pure quartz, and progressively we move into what we call the inner zone, which is dominated by quartz and feldspar. We can find also mica. In the nucleus, the crystals are several meters long, while in the inner zone they are only a meter or slightly less in size. Then moving toward the host rock, we reach the intermediate zone dominated by mica. We can find also quartz and feldspar. And again, the size of the minerals decrease, and we have about 10 centimeters long crystals. And finally, close to the host rock, we have the marginal zone, where we have tourmaline and mica, plus minus quartz and feldspar. the crystals are few centimeters to millimeters long only. So that's an example of mineralogical and textural zoning in pegmatites. How the LCT pegmatite deposits form. They are the result of the very last stages of fractional crystallization of a granitic magma. Basically, when a magma begins to crystallize, the first minerals formed are olivine and pyroxene and calcium-rich plagioclase. They are denser than the remaining liquid, and they sink at the bottom of the magma chamber. As a result, the liquid, the remaining liquid, is more enriched into the elements that are not included in olivine, pyroxene, and calcium plagioclase. Specifically, incompatible elements like lithium, at some point as the crystallization goes, the lithium content and other incompatible element contents are so high that the liquid reaches saturation, and lithium bearing minerals start to crystallize. Because the first mineral formed during crystallization are dry, fluids remain into the remaining magma. So at the end of the crystallization, we have a lot of fluids. We have water, we have halogens like fluorine and chlorine. Nevertheless, the origin of the fluids involved in the formation of pegmatite deposits is still debated. We still don't know if it is only from the magma itself through fractional crystallization, as I explained, or if the fluids come from somewhere else. The origin of this initial granitic magma is the melting of an aluminous gneiss or schist. It's a metamorphic rock with a sedimentary origin. To be accurate, this is a S-type granite composition for the initial magma. In terms of geodynamical setting, we find LCT pegmatites in subduction and continental collision settings. Now I will briefly talk about one specific LCT pegmatite deposit, the Greenbush Mine in Western Australia, because this is the largest pegmatite body mined presently. The Greenbush Mine is located here, about 250 kilometers south of Perth here. And this is the Cornwall open pit, as it was in 2012, and the pegmatite body is here. Few details about this deposit. It's a spodumene deposit, the largest mine operation for lithium in the world. The pegmatite is a giant dike. It formed in the Archean time, about 2,500 million years ago, and this pegmatite dike is intruding an amphibolite, which is a metamorphic rock. The pegmatite has a granitic composition. It's 250 meters long and between 60 to 2,500 meters wide. It's associated with a metamorphic event. We believe that the temperature of crystallization was between 550 to 625 degrees. It happened during an intense stage of deformation. We have a lot of faults, and in this area we have a lot of evidences of fluid circulation. The main ore minerals in the Greenbushes deposit: spodumene, cassiterite for tin, and tantalite for tantalum. The mining operation started in 1986 for tin. From tin, mining switched to tantalum, then in 1985 to lithium. Actually, tin mining stopped in 1983. Lithium now is the main target of the mining operation. As I said, the largest spodumene mine in the world, and about 80 kilotons of spodumene were extracted in 2019, and that's the highest lithium grade in the world, locally up to 5% of lithium oxide. The estimated resource, 0.85 million tons. Now let's have a look at the other type of pegmatite deposit. This is a large heterogeneous group of rocks. We have a specific type of pegmatite, the NYF pegmatites for niobium, yttrium, fluorine, enriched pegmatites. In this group of pegmatite deposit, we have also alkaline pegmatites like Mont Saint-Hilaire in Quebec. And we have also metasomatized rocks associated with these pegmatites. We can observe also mineralogical and textural zoning in these pegmatites, and they are sources of other valuable elements: niobium, yttrium, zirconium, titanium, scandium, rare earth elements, uranium, thorium, fluorine. In terms of lithium-bearing phases, we have lepidolite, elbaite. 1/3 of the known lithium-bearing species are actually present in these rocks, but they are less abundant compared to the LCT pegmatites. So these pegmatites are economically less interesting than the LCT for lithium sourcing. The origin and formation of the non-LCT pegmatite deposits. The formation, again, the very last stages of fractional crystallization of a granitic magma. To grow these minerals, we need fluids, water, halogen. The origin of the fluids is also debated from the magma itself as a result of the very advanced fractional crystallization, or from somewhere else, from the country rock. This is still debated. The origin of this initial granitic magma, several hypotheses. That could be melting of an igneous rock during a subduction, that what we call I-type granite composition, the evolvement of such magma is debated in the origin of the non-LCT pegmatites. Another hypothesis is the involvement of melting of lower crust in a post-collision setting. This is what we call the A-type granite composition. And there's non-LCT pegmatites could be also formed by direct differentiation of a mantle-derived basaltic melt through fractional crystallization, and that would happen in an interplate geodynamic setting. So that will be it for the pegmatite deposits, and now we switch to the second most important lithium deposit, which is the brine deposits. The brine deposits, they are formed by evaporation of brine. Brine is a solution containing salts in concentration exceeding more than 3.5%. Brine deposits are what you have seen in the previous slides. It's salars, salt pans, salt flats. The usual lithium-bearing minerals are chloride salts, and we can find also valuable elements like boron, potassium, and sodium. Most of the brine deposits are located in South America. That's the lithium triangle. That's Argentina, Bolivia, and Chile. That's more or less the Atacama Desert. These deposits are quite large, and they have low lithium grade, less than 0.28% of lithium metal. However, as I already mentioned, they represent about 60% of the worldwide resources, but only 40% of the current production. In fact, 35% of the current production is originated from 2 salars in Chile. Now we can look at the models of brine deposit formation. We need an arid climate. We need a closed sedimentary basin, and we need lithium contents of 200 to 1400 ppm in the brine. Lithium is highly soluble. It does not form readily evaporate minerals. Then it concentrates in the remaining solution. So we need suitable sources of lithium and sufficient time to concentrate lithium in brine. The potential sources of lithium are still debated. Could be the country rock, could be the magmatic or hydrothermal fluids, could be the alteration of volcanic deposits, it could be also sediments, and also could be groundwater. This is the formation of brine deposits are illustrated by this diagram, and mechanism for removing lithium from the brine pool or spills out of the basin, leaks through the bottom of the basin, and formation of clay minerals, and finally lithium trapped into fluid inclusions. Now let's switch to sedimentary deposits. That's clay deposits. We can distinguish three main types. The hectorite type deposits. Hectorite is a clay mineral with this kind of chemical formula, and that is the main lithium phase in this kind of deposit. We have also deposits formed by mixed halite smectite deposits. We call them iron clay deposits. I will not insist on this term. And what we see from different studies is that there is a continuum in terms of type of clay minerals occurring in these two deposits. The third subtype of clay deposit is the jadarite type deposit from Jadar in Serbia. It's unique in the world, and the main lithium phase is jadarite. It's a boron silicate with this formula. The formation of clay deposits is not well constrained. It seems to be always associated with nearby rhyolite lavas or rhyolite tuff deposits, and there is always the presence of hydrothermal activity. Finally, the last type of lithium deposit, metasomatic deposits. These deposits are directly related to hydrothermal fluid circulations. The origin and formation of these deposits is not well understood so far. As I said, this type of deposit has been recognized as such very recently. We can distinguish two main types of metasomatic deposits: manganese-rich sediments transformed by circulation of hydrothermal fluids. The formation of this kind of deposit is related to a metamorphic event, and the lithium-bearing minerals occur as veins and fracture fillings, and the main type is sugilite. It's a tourmaline mineral. There is another type of metasomatic deposit, and it is formed by metasomatized magmatic rocks, but not related to Pegmatite Formation. And there is always the involvement of metasomatic or hydrothermal fluids in the formation of this type of lithium deposit. So far, these metasomatic deposits are not economically interesting because of low grade. At least it's not economically interesting for the moment, considering the market price. As a summary of formation processes of lithium deposits. As I said early on in this lecture, lithium is an incompatible element in magmatic processes and soluble in fluids. It stays in liquids. Through magmatic processes, fractional crystallization of the magma, that's the production of magmatic rocks, as I said, as crystallization proceeds, newly crystallized minerals are separated from the remaining liquid, which is enriched in incompatible elements, and that includes lithium. That's why pegmatites are so enriched in lithium and other valuable elements. We have also fluid processes, hydrothermal, high temperature circulation of solutions, and we have also surface, subsurface alteration processes of pre-existing rocks by aqueous solution, and this is what we see in the formation of the clay lithium deposits. Okay, this is the last slide of this lecture, the summary of the lecture. Lithium is a rare element in our universe. Lithium is more abundant in the crust of Earth compared to the mantle. Lithium is present in silicates. Lithium pegmatites are presently the main source of lithium. They have the highest ore grade and reserves, but brine deposits have the largest resources, but these deposits are not fully exploited.